Hello everyone, this is the second video in our playlist, and in this part of the video we're going to discuss something related to the increase of our air bubble particle and decrease in temperature. So we're given a question, and in the question we are given that assume that the decrease in air temperature with altitude can be modeled entirely by adiabatic reversible expansion of pocket of air, which is ideal gas, right? Starting from the basic equation of fluid statics. And we're asked to derive two things. So the first thing is the air pressure as a function of altitude, and the second thing is air temperature as a function of altitude. So from the basic equation of a fluid statics, we know that the dP over dz is going to be equal to the rho times acceleration, which is the density times acceleration, right? And when our height is increasing and the gravity is going to act downwards, right, we're going to have an equation of negative rho times g. And what I can do now is I can replace density by negative Pm over RT times G, right? And so we have this equal to this one, right? But it is considering a very small change in pressure and very small change in height, right? So what I can do now is I'm gonna replace the how it looks like. So I can say that it's gonna be dP over pressure, and I can say that it's negative mg RT times dz, right? So I just multiplied both sides by dz and divided both sides by the pressure. And if I want to find how they are related, I'm gonna have to take the integral of it. So for the pressure, it's gonna be dummy variable of integration, and for the pressure we're going to start from the atmospheric pressure, which is 301 and 1125 pascals to some pressure of P. And for the Z, we're going to start from 0 to some height of Z, right? And when we find the integral, it's going to be ln of p is going to be equal to, so for this part it's just going to be like negative mgz over rt, right? And our pressure is going to be represented as the oops, I forgot, like this one. So it's just ln of p minus ln of 101,325, right? And yes, and our function for the p is going to be represented by this equation, e to the power of negative mgz over rt, where e is the exponent, okay? So now we know how the pressure relates with the height, right? And in our case, we're given a air particle, a pocket of air, and we're saying that it's an adiabatic process. So changing heat is 0, right? It's 0, and we also have some kind of pressure of it. And what we also have is it's an ideal gas. We're given that it's an ideal gas. And from the first law of thermodynamics, we know that our du is going to be equal to our dq minus pdv, right? And for our specific case, our du is going to be equal to the specific heat capacity at a constant volume times dt. And our dq is going to be equal to 0 because it's an adiabatic process, right? And I'm going to replace pressure with the like RT over V from the equation like PV is equal nRT. Okay, it's going to be negative RT over V dV, right? And if I want to, we're still considering a very small amount of volume and very small change in temperature. So if I want to find a relationship, I'm gonna take integral from both sides. So for the temperature, let's say we're gonna start from T1 to T, and for the volume, it's just gonna be negative T. Oh, here I just realized that before taking the integral of temperature, I could have divided both sides by the temperature, and so this is going to be negative R dV over V. And where for the volume, we're also going from some volume of V1 to another another volume. Okay, when I take the integral, so this thing is going to become CV ln of t, right? No, it's going to become ln of t over t initial. And it's going to, for the right hand side, it's going to become r v over ln of v, this thing. So this is what we get from the integration of our equation. And the next step we have to do is we're going to change how it looks like a bit. So I'm going to divide both sides by r. And what I'm going to have is, so the specific heat at constant volume over r. And it's going to be ln of t over t initial equals ln of negative ln. So I'm going to get that negative inside of our logarithm. So it's going to be v initial over v. So I just replaced so the negative inside of logarithm is going to go to the power of something inside of a logarithm. So the negative power is just going to make it opposite. So we're going to have initial volume over volume. And the next thing is I'm going to take the exponent from the both sides. So I'm going to have t over t initial to the power of cv over r. And for this part, I'm going to have v initial over v, right? And now we are considering the relationship of a temperature with the volume. But what we can do now is we can change the volume to RT over pressure so that we can find the relationship of a temperature and pressure. So I'm going to express that as RT initial over pressure initial over RT over pressure. And R is going to cancel, and what I'm going to have is, for the right hand side, I'm going to have T, so it's Ti over T times P over P initial, right? And what I can do is I can move this to this part of our equation, right? And what we are going to have is, so when I'm shifted here, it's going to be the opposite. So we have 1 added to the power. It's going to be equal to pressure over initial pressure. Okay, so the next thing we're going to do here is, we know that the specific heat constant at a constant pressure, Cp, is going to be equal to the specific heat at a constant volume plus R, which is the constant, right? Ideal gas constant. So, and I can, if I consider only this power, so Cv over R, if I'm going to multiply both sides by R, like both terms by R, it's just going to be, right, if I give the common denominator. So I can replace this part by the specific heat constant at a constant specific heat constant at a constant pressure. So it's just going to be Cp over R. Okay, and then our equation is going to look like in this form. Okay, the next thing is, so now we have this equation, and if I decrease the right hand side by this power but the opposite, so what I want to do is I want to make t as the subject of our equation, so it's just going to be like ti over t to the power of like pi to the power of r over cp, and then our t is going to be equal to ti here. I noticed a mistake. So when I was writing it down, it was t, it should have been t over t initial, not t initial over t. So our equation should change here. So our equation for temperature is going to become pressure over initial pressure, R over specific heat constant at a constant pressure. Yes, so that's what we have for our temperature. And now, as I have this equation, I can replace that by this equation here. So I'm just gonna get that temperature and plug in this one, okay? And what I'm gonna have is, so for this side, I'm gonna have just dp over dz. And for right hand side, so it's negative pm over negative pmg over RT R. But for the temperature, when we plug in this temperature, this Ti is gonna stay in here, right? And the pressure, so we have one pressure here, and it's gonna become like 1 plus to the power of of our pressure. It's R over Cp plus. No, it's gonna become 1 minus because we're dividing by P. R over Cp, and for our P initial, it's just gonna be the R over Cp. Yep, they should be fine. Yeah, this is correct now. Okay, and what's next? So I'm gonna move the pressures to this side and dz to this side, to the right hand side, and to kind of change how it looks like just with this equation. Okay, I'm gonna move the pressure to this side, so it's just gonna become like, it's just gonna become pressure. So we're gonna change the power of it, so it's just gonna become R over Cp minus 1 when we shift it to this side. Yep, and dP equals mg over RT initial pressure R over Cp and dz. And I'm going to integrate it from initial pressure to the pressure to some pressure, and for this one I'm going to integrate it from let it be from z initial to some height of z. Okay, and I'm going to make it a dummy variable of integration. Okay, when we take the integral, it's going to become So this something, so the power should go to the down, right? So I'm gonna have R, like Cp over R times pressure R to the Cp from the initial pressure to the second pressure. And for this side, when I take the integral, it's just going to become z multiplied. But we're going to consider we're not starting the height from the zero, so we're going to have to consider like change in the actual change in height. So I'm going to leave it as z minus z initial. So it's going to become z minus z initial. Okay, I can now move this to this side of our equation, and I can divide, before that, I should replace the variables here, right? And I'm gonna divide everything by Cp over R. Okay, so these R's are gonna cancel, and what I'm gonna have for the left hand side is P R over Cp minus P initial over R Cp, and for this side I'm gonna have, you know what, I think I did another tiny error. I forgot this negative sign here and here and here. So mg over Cp T initial, so the r's got cancelled, right? And we have this pressure. I also forgot this initial value here. Yep. So R over Cp z minus z initial. Okay, the next step is, so we were deriving the relationship, so we were deriving a function of a pressure respect to the height, right? So I'm just going to move this to this side of our equation, right? And I'm going to factorize it by this pressure. So we're going to have two pressures, so I'm just going to factorize the right hand side. So our P, RCP is going to be equal to P initial RCP, and so it's going to become 1 minus mgCpt and z minus z initial, right? And if I want to find the pressure itself, I'm just going to have to increase both to the power of Cp over R. So it's just going to be pressure initial, and the power gets cancelled because of this effect. And I'm going to have to increase the bracket to the power of Cp over R. Cp over R. And this thing right here is gonna be the answer for our first part of our question. So we now derive the expression for the air pressure as a function of altitude, where our altitude is z and this p is just a pressure. Okay, so now in the second part of our question, we're asked to find the temperature as a expression for the air temperature as a function of altitude, right? And here I remember deriving a relationship of a pressure and temperature. So this equation right here, this one, yep. So this equation, we already derived it, right? So what I'm gonna do is I'm just gonna replace this pressure by the expression of air pressure as a function of altitude. So I'm just gonna plug in the whole expression instead of P. So it's just going to be T is equal T initial times P initial, and this whole equation in numerator, P initial 1 minus mg Cpt z minus z initial, right, to the power of Cp over R. And in our equation we have, in our temperature and pressure equation we have everything increased by R over Cp. So these pressures are gonna get cancelled, and the power is exactly the opposite of each other, so the powers are also gonna got cancelled, so they also got cancelled. And the temperature equation we have is now gonna be the initial temperature at some height is going to be equal to 1 minus mass times the gravitational acceleration, specific heat constant at a specific heat capacity at a constant pressure times temperature, and the change, so a final height minus the initial height. And that's going to be the answer for our second part of our question. So we now derive the expression for the temperature as a function of altitude. Thanks for your attention.